Hi, everyone. Um, my name is Duke, and today we will present our latest work, AutoCoG, a unified data model code search framework for graph neural networks. In this talk, we'll first go over the introduction, which includes the motivation and contribution. Then we'll discuss our approach, our problem formulation, our architecture graph code search, as well as our search base. And finally, we will discuss the different experiments that we performed. The motivation behind our work is that training for graph neural network is known to be notoriously challenging, more so when you are trying to train under a heterophily or dissociative graphs. Since graph abstract diverse data sources and present tremendous heterogeneity, the success of a graph neural network is often accompanied by extensive tuning of model architecture hyperparameters to characterize specific graph data. In the real world, graphs often opposite attract, which inevitably lead to noisy settings where GNN tend to suffer from overfitting and generalize poorly due to unseen testing data. And finally, despite the potential of deep graph neural network in learning the informative high-order neighborhood, the training of deep GNN is widely known to be limited by the issues of oversmoothing, gradient vanishing, and oversquashing. Our contribution is as followed. Our proposed framework is the first NAS framework toward a unified data model code search for GNNs. Our bi-level optimization formulation uniquely enables the end-to-end discovery of GNN neural architecture and graph topology altogether. We perform an extensive amount of analysis on the resulting learned graph structures for each benchmark. And to strengthen the code search framework, we also organically integrate several different techniques to directly combat the issue of searching unreliability, training instability, as well as scalability. And also, we also show that experiments achieve an average performance gains across all the set for all of the benchmark we compare against. And overall, we also rank the best against all state-of-the-art methods with the average ranking of about 2.5. So to summarize the objective goal of our data model code search, we shall use a two-layer GNN node classifier as an example. Here, we summarize the classification process as the softmax function of the nested of two nested function, where Z is our output, and the nested function represents each individual GNN layer. We can see that the objective goal for AutoCoG graph is to find a search model, which we shall simply represent as the as W hat, representing the supernet from our search space multiplied by some masking matrix, which can be derived after the searching process. And also, we also include a augmented graph, which similarly is the masking of the original adjacency graph. So continue from the previous example, we shall denote the node classification objective loss given here. And therefore, we formulate our bi-level search function as the process of trying to find the alpha parameter, which is our architecture parameters based on the value objective loss, using the weight obtained by the following objective loss based on the training process. Here, we shall illustrate the overview of our data model code search, AutoCoG, where our search space is illustrated by the yellow blocks in which we search for the attention, skip, and activation. And for each of the skip connection, we search for either the jumping connection or the knowledge skip connection for final aggregation. Note that for each progressive stage, we would truncate our search space by eliminating the worst performing choice. And at the same time, we would augment the original graph. For the model search space, we search the attention search space, which if you look to the right for table 1, we search for the GCN, cosine, linear, generalized linear, gate attention network, the sum gate attention network, as well as constant. We also search for different activation search space, including but not limited to ReLU, sigmoid, tan, etc., as well as the different skip connections, such as the initial connection, as well as jumping knowledge aggregation. For how do we do graph augmentation? Following our adjacency matrix formulation, where S is our scoring matrix, the augmented graph is illustrated as the masking function of the original adjacency matrix multiplied by some scoring function, where the scoring function is obtained by simply by simply learning an MLP function on the concatenated embeddings of the source and target nodes, where the function is simply an embedding of an intermediary layer of our search GNN, Z V source and Z V target simply is the hidden embeddings. And we denote the concatenation as 2 dash. Taking advantage of the progressive NAS workflow, at each setting stage, we prune the bottom P percentile from the scoring function. And at the same time, we randomly grow our graph by appending K new edges for each node via the embedding similarity. The embedding similarity is given by the equation below, where it is simply 1 plus for the cosine similarity divided by the log of the shortest distance between 2 nodes. Here we illustrate our experimental result. We summarize our average performance using the average improvement and average ranking, where the average improvement illustrates the percentage improvement of our work relatively to the current model, average across all data sets. So higher is better. Average ranking, on the other hand, illustrate the relative ranking of each model to everyone else. So lower is better. So in both metrics, we can observe that AutoCoG graph consistently improve on every other framework, as well as consistently rank highest for all dataset. We also perform several ablation studies to verify the different aspect of AutoCoG graph. So in this study, we compare the test result between different searching mode at increasing degree of homophily with fixed depth at 8. So we can see that with co-search, we obtain the best result relatively to only data search and model-only search. We also want to verify whether or not our graph search can improve the robustness. But first, by taking the original graph, we add random noise edge to the percentage amount with respect to the total edge specified by each column. So as can be observed on Texas, Wisconsin, and Cornell, with co-search, we consistently rank higher than without, which demonstrate the ability of AutoCoG in reducing noise. Moreover, we also study whether or not progressive search is necessary by comparing the performance at various GNN depth search with and without. So as we can see, with increasing depth, without progressive search, we get increasingly worse result due to model instability. But with progressive search, we can definitively improve the stability and keep the result consistent. Finally, we characterize the efficiencies and effectiveness of our search method by measuring the memory usage and total runtime to search and fully trained model at various datasets. And as you can see, AutoCoG consistently perform faster and use less memory than other search methods such as SAN and GraphNAS. This concludes our talk. Thank you for listening.